доклад Михаила Грабчака. Это доклад совместный с Исааком Сонином. Мы их хорошо знаем, они уже неоднократно выступали на нашем семинаре. Доклад сегодня, ну, название вы видите, «Закон нуля и единицы для марковских цепей, однородных и неоднородных, насколько мы знаем из аннотации». И доклад сегодня будет на английском, но, насколько я понимаю, Михаил, подтвердите, вы же, если вопросы будут задаваться на русском языке, это возможно?
Я знаю, я могу немножко говорить по-русски, поэтому я понимаю, ну, когда с математикой, может быть, не все, но, конечно, можно по-русски тоже.
Хорошо. И еще, коллеги, как всегда, я прошу вас, у нас разрешается задавать вопросы по ходу доклада, но сейчас я прошу выключить все, отключить звук микрофона и остановить видео, чтобы не было нагрузки.
Ну и вас не слышно.
Да, Лена, вы себя выключили.
Да, я сразу выключила. Я еще раз говорю, уважаемые коллеги, мы сейчас отключаем звук и видео, чтобы не было нагрузки на сеть.
А вот. Я не умею.
Лариса Григорьевна, Гриша сейчас отключит.
Его нету.
Вот.
Так что терпите, меня терпите. Я не буду возникать.
Хорошо, ну вот на всякий случай. А если захочется вас задать вопрос, то тогда, пожалуйста, подключайте звук. Михаил, пожалуйста, начинайте. Приглашаем вас.
Хорошо, спасибо. Thank you for giving me the opportunity to give a talk at this seminar. It's a very, of course, well-known and very famous seminar, and I feel very, very honored to give a talk here. This, of course, is about the 0-1 law for Markov chains and related topics. And of course, at any time, please ask any questions that you have. I'm more than happy to address them at any time during the talk. This is joint work with my colleague, Isaac Sonin. He's here for a few minutes. He has a class in about 15 minutes, so he won't be here for long, but he's here for a little bit for this talk. And so this is joint work with him. So the talk is going to be in three parts. The first part will be the 0-1 law for Markov chains. And then the second part is going to be kind of a question. It's not very mathematical, but more about kind of how do we define Markov chains if the Markov chain, instead of going in forward time, is going in backward time. And can we really think about Markov chains going in backward time in the same way we think about Markov chains in forward time? Again, this won't be anything too new, but perhaps ask some questions that not everyone has thought about. And the last part is about the existence of Markov chains indexed not by the integers, not by the natural numbers where we have a clear starting point and go forward, but indexed by the integers or just the negative integers where there is no starting point. We just kind of start at -infinity and go forward in time. So not going backwards, but forward, but without a starting point. And under what conditions do such Markov chains exist? And all of these questions kind of came from our work on the 0-1 law for Markov chains. So let's get started with the first part, a 0-1 law for Markov chains. And first, let's recall the classical Kolmogorov's 0-1 law. So let x0, x1, x2, and so forth be a sequence of random variables. And we define, as usual, the tail sigma algebra. The idea of the tail sigma algebra is that these are events that are determined by the sequence, but no finite subcollection of the random variables determines these events. So these are events that don't depend on any finite subcollection. That's the tail sigma algebra. And of course, Kolmogorov's 0-1 law tells us that if the random variables are independent, then for any event A in the tail sigma field, the probability of that event will be either 0 or 1. This is, I suppose, on the one hand, a kind of technical result. On the other hand, it's a very useful result that gets to certain truth about independent random variables. And might be interesting to note, just to talk about how important this result is, there's a famous textbook by Struck on kind of advanced probability. And this Kolmogorov 0-1 law is the very first theorem in the book. It's on page 2, I think, just to give you perhaps some idea of the centrality of this theorem. So, of course, an obvious question to ask is, do we still get the 0-1 law if we don't have independence? And certainly we would not expect to have such a result, such a strong result without some kind of assumption. So of course we need some kind of extra assumptions. And many people have studied this question of what other kinds of assumptions we might need to get a 0-1 law for a sequence of random variables. This is just a survey of just a few papers in this area. There's quite a bit more in the literature of extending the 0-1 law to other situations. Now, of course, we're interested in 0-1 laws for Markov chains. And so for a Markov chain, do we still get a 0-1 law? And again, not without some extra assumptions, as we would expect. So first, let's ask the question, what can go wrong? Why would we not get a 0-1 law for Markov chains? What kind of behaviors would a Markov chain have that could preclude that? And before answering or dealing with this question of what can go wrong, maybe this is a good idea to just pause and recall the definition of a Markov chain. Now, I'm absolutely certain everybody here knows what a Markov chain is, but I was told some students might come, and so it would be good to be able to talk about things a little bit more basically. And secondly, I want to make sure we're all on the same page, because there's maybe different ways to think about a Markov chain. So for us, we'll think of a sequence of random variables. It's called a Markov chain. Of course, we're talking about discrete time, discrete state space, but a sequence of random variables is called a Markov chain if it satisfies the Markov property. That is to say that the probability that at time n we're in a certain state, given the entire history, is the same as the probability of being in that state, given just the most recent observation. The past history does not matter. And of course, a Markov chain is called homogeneous if, in addition, for every n, this probability does not depend on n and would be the same as going from time 0 to time 1. So now with this definition solidified, why would a Markov chain not satisfy the 0-1 law? So here's a simple example with an absorbing Markov chain. So assume the dynamics of the Markov chain are determined by this transition diagram. So there's 3 possible states, A, B, and C. When we're in state A, with probability half we go to B, with probability half we go to C, and then if we're in state B, we just always stay in state B, and if we're in state C, we always stay in state C. So let's assume that with probability 1, we always start in state A, and consider the event E, which is the event that we visit state B infinitely often. Well, if we ever get to state B, we'll certainly visit state B infinitely often. But if we don't get to state B and get to state C, then we won't visit state B infinitely often. Now, event E is in the tail sigma field because this event does not depend on any finite collection of random variables, right? It's only determined by the sequence overall, but not by any finite collection of random variables. So event E is in the tail, but its probability is neither 0 nor 1 because, well, since we start with probability 1 in state A, with probability half we go to B and stay there. So the probability of E is 0.5, not 0 or 1. So we can see how the 0-1 law will not hold for an absorbing Markov chain like this. Another example where we don't have where the issue is not with being absorbing, consider this Markov chain. It's almost deterministic. We just kind of keep going around in a circle. The randomness comes in with where we start. So where we start will be random, which state. Now let's consider event F to be the event that we visit state B on infinitely many even steps. Now, of course, we will certainly visit state B infinitely many times, no matter where we start. But the only way we'll visit state B infinitely many times on even steps is if we start either in state B or in state D. If we start in state A or state C, we'll only visit state B on odd steps. Of course, this event is in the tail because it's not determined by any finite collection of random variables. And the probability of F is, well, the probability we start in state B or D, which, depending on how we choose that probability, if it's not 0 or 1, will not give us a 0 or 1 law for this event. So this is another situation where the 0-1 law no longer works, and here the issue is related to randomness in where we start. So with these examples in mind, we can formulate Blackwell and Friedman's 0-1 law for Markov chains, which says that if Z0, Z1, Z2, and so forth is a homogeneous Markov chain, and if it is recurrent, and the probability of us starting in a certain state is 1 for some state, then for any event A in the tail, the probability of A is either 0 or 1. So under these conditions, we will have a 0-1 law. And note specifically, we have a recurrent Markov chain, which precludes situations like what we had in our first example, right? Recurrent means that we will visit every state infinitely many times, and that is not something that could happen with our first example. So this recurrent ensures that we don't have the situation we saw with the first example. And then the probability Z0 equals I is 1 ensures we don't have the situation we saw with our second example. Okay, now this of course is not very general. This is just for homogeneous Markov chains. There are some conditions. More generally, a Markov chain satisfies the 0-1 law if and only if it satisfies a certain type of mixing condition. You can find the details in Blackwell and Friedman 1964. So the question is, what can we do more generally if we don't have mixing? Well, if we don't have mixing, then there will certainly be, or there could be events in T with probability not equal to 0 or 1, and we saw such examples. But here's the interesting observation. If we look at the problem from a different perspective, we still see something like a 0-1 law nevertheless holds. So if A is in the tail, then for large n, the probability of A given Zn, this conditional probability, will be close to 0 or 1 with high probability. So it won't be equal to 0 or 1, and this is only for large n, but it will be close to 0 and close to 1 with a high probability. So it's a maybe it's not quite fair to call this a 0-1 law, but it suggests that there's some kind of 0-1 law underpinning this nevertheless. And this fact, as it turns out, will be true no matter what the Markov chain is, whether it's homogeneous or non-homogeneous, finite or countable, won't matter. This result will be true. So we'll call this result a 0-1 law for Markov chains, even though, of course, it's not quite talking about the same thing as Kolmogorov's law, and it's somewhat a different perspective. Now, this law is due to my collaborator, Isaac Sonin, and it was originally published in his 1991 paper. And it is a byproduct of the proof of his decomposition separation theorem. Now, those who don't know, Sonin's decomposition separation theorem is a pretty interesting result. It's difficult to state it mathematically, or at least it requires defining a lot of terms, so I won't give it here, but just want to mention that it is an extension of the idea of classification of states to the case of non-homogeneous Markov chains with no assumptions placed on the sequence of transition matrices. So basically, the idea of ergodic states, transient states, recurrent states can be extended to non-homogeneous Markov chains without any kind of assumptions placed at all. So that's the decomposition separation theorem. You could find that in Sonin's work. Now, the 0-1 law for Markov chains, to state it more formally than that kind of short sentence that I had on the previous slide. So let's assume we have a Markov chain, Z0, Z1, and so forth, finite or countable, homogeneous or non-homogeneous Markov chain, fixed in event in the tail. And for any A between 1 and 2 consider the collection of states such that the probability that that event A happens, given that at time n we're in one of these states. So Sn of AB is the collection of all the states for which this conditional probability is between A and B. And the basic thrust of this theorem is that if A and B are bounded away from 0 and 1, the probability that asymptotically we will see a state for which the probability of this conditional probability is bounded away from 0 or 1 is 0. So asymptotically, we're not going to see such a state. So that's the idea of this 0-1 law for Markov chains. Again, very different perspective than Kolmogorov's, but still tries to get at the idea that there's some kind of 0-1-ness underpinning even this very general situation, although again, in a very different perspective. So this means that for large n with probability near 1, the trajectories of our Markov chain, Zn, are in states where the probability of A, given that we are in that state, is either near 0 or near 1. Now, the proof was given in Sonin 1991, but when we came back to it just maybe a couple months ago, we found that the proof was incomplete. It had gaps. Took us a while to figure out how to reconstruct it. And so we tried to clarify it. And in the paper, we clarify it. We give 2 detailed proofs. One that's kind of a slick proof, but requires some more advanced tools and doesn't really get to the heart of why this is true. And another one that really tries to explain why it's true. So you could find those in the paper. I won't discuss them today, but you can find the proofs in the paper. Now, there's a more general version of the law. So, of course, what I gave was part B here, that the probability of being in a state for which we're bound, the conditional probability is bounded away from 0 and 1 goes to 0. And then the probability of being in a state close to 1, that goes to probability of A. And the probability of being in a state close to 0, that goes to probability of A complement, or 1 minus the probability of A. Further, one can, the result is not just true for probabilities. We have convergence at the level of events. So the event that we see a state, let's say, bounded away from 0 and where the conditional probability is bounded away from 0 and 1 goes to the empty set, whereas the other cases go to the appropriate sets as well. So there's a more detailed version in terms of convergence of sets. Okay, so after we looked at the 0-1 law for Markov chains from this perspective, we asked the question kind of what happens in the context of the entrance sigma algebra. So if we have a Markov chain, or more broadly, let's first consider in a more general framework. Let's just consider we have a sequence of random variables indexed now not by the natural numbers, but by the integers. So this sequence doesn't have a starting point. It starts at -infinity and goes forward in time to +infinity. So we have this sequence of random variables. And now, instead of the tail sigma algebra, we talk about the entrance sigma algebra, which is what happened near -infinity. So the idea is that this sigma algebra is what, it doesn't depend on any finite collection of random variables. It does not depend on any infinite collection that's close to infinity. It only depends on random variables close to -infinity. So the events in this tail sigma algebra only depend on the random variables close to -infinity and none that start from some finite point going forward. So now first let's formulate Kolmogorov's 0-1 law for the entrance sigma algebra. So if the random variables are independent and A belongs to the entrance sigma algebra, then the probability of A is 0 or 1. Kind of obvious that this would be true. This is a statement. So first, in Struk's book, he actually mentions Kolmogorov's law in such a way that it would cover this results, and kind of obvious why this should be true. I want to give the proof, not because the proof itself is in any sense complicated, but it gives us an idea of how to approach the 0-1 law for Markov chains and try to prove that result. So the idea is to reverse, starting at time -1, just kind of reverse the flow of time and go in the negative direction. So consider the random variable y1 to be x -1, y2 to be x -2, and so forth, going in the negative toward negative infinity. Of course, these random variables are still independent, and and now their tail sigma algebra is the tail sigma algebra of the y's is the entrance sigma algebra of the h's. So we can directly apply Kolmogorov's 0-1 law to get the result. Again, kind of obvious proof, but shows how to do a similar thing for the 0-1 law for Markov chains. So now let's formulate the 0-1 law for Markov chains for the entrance sigma algebra. First, we need to think, well, what do we mean by a sequence of random variables indexed by the integers, which is a Markov chain? So again, for us, this will mean that the Markov property holds, just as before. So the probability xn is in some state given the entire history. But notice now the history is not going till some starting point at time 0, but it keeps going all the way to -infinity. And this probability of Zn being in some state given the entire history going to -infinity is just the probability of being in that state given the most recent observation. And of course, we can think about homogeneous Markov chains indexed by the integers in a similar way. So now that we have some idea of what a Markov chain on the integers indexed by the integers means, we can talk about, okay, let's consider a Markov chain on the integers, finite or countable, homogeneous or non-homogeneous, fix any event in the entrance sigma algebra, and again, for any a and b between 0 and 1, consider the collection of states such that if at time n we're in such a state, the probability of a given being at time n in this state is between a and b. And again, if a and b are bounded away from 0 and 1, the probability of being in such a state goes to 0. Now, of course, instead of n going to +infinity, it goes to -infinity, and we get the other results as well. And as in the previous case, the convergence is in terms of events and not just in terms of probabilities. And the proof is exactly what we saw with the Kolmogorov 0-1 law. We consider re-indexing this to look at -infinity as kind of being positive. So y1 is equal to z -1, y2 equals z -2, and so forth. It's not difficult to show that the y's still form a Markov chain in the sense that they still satisfy the Markov property, and their tail sigma algebra is going to be the entrance sigma algebra, so we can just apply the 0-1 law for Markov chains directly to get the result. So that's the idea here. Nothing too complicated. But in having this perspective of thinking what happens at -infinity, it led us to two questions, which will be what the rest of the talk is about. The first is, within this proof, we had to define these y's going in the backward direction, and we said they still form a Markov chain. But even though they still form a Markov chain in the sense that they still satisfy the Markov property, they don't. It led us to the question: what is the transition matrices for the Markov chain in backward time that we have here? And they don't really. And the issue is they don't really exist. And so this kind of brought up the question: can we really think of it as a Markov chain? And what exactly is the right way to think about a Markov chain? So that's the first question. And of course, the second question is we kind of postulated this Markov chain indexed by the integers, but does that exist? Well, it will exist, certainly, but under certain conditions. So under what conditions can we have a Markov chain without a starting point that just starts at -infinity and goes to +infinity? So those are two questions that we wanted to answer that kind of came about from us trying to understand this 0-1 law. So let's talk about part two. Is a Markov chain in backward time really a Markov chain, essentially? So first, here's a question. Does everyone agree on what a Markov chain is? And I'd say in forward time, probably most people will agree on what a Markov chain is. But in backward time, maybe not. And this kind of came about from some discussions with Isaac Sonin, my collaborator on this work, where between the two of us, we didn't completely agree on how we thought about a Markov chain. So that's what made us think a little bit more about this question. So again, the way I defined a Markov chain earlier in this talk is in terms of the Markov property. But another way that people often think about Markov chains is that we have some initial distribution pi and a sequence of transition matrices. If the Markov chain is homogeneous, the sequence is just one matrix. Otherwise, for a non-homogeneous Markov chain, it's a sequence of transition matrices. Pi, the initial distribution, tells us the probability. So, if we're starting at, so let's say we're starting at state 0. In this case, not thinking about being indexed by the integers, but just the usual standard situation. So then we have an initial distribution at time 0 given by pi, and then p sub n, the ijth coordinate of matrix Pn, gives us the transitions from time n to time n plus 1. So we have a Markov model, and we have this Markov property definition, and they're not quite the same. We're maybe sometimes used to think of them as being very similar. They're usually in many textbooks on undergraduate and even master's level probability. They're kind of presented together, but that doesn't mean that they're the same. So, so in forward time, they kind of behave the same way, but not so much in backward time. And I should mention that a corresponding situation is true for homogeneous Markov chains, that I kind of alluded to. Okay, so when we have this Markov model, if we start with a Markov model and then consider looking at the going in backward time, the Markov property will still hold. And by Bayes' rule, what's going to happen is that the probability xn equals j, given that xn plus 1 was I, well, by Markov's, sorry, not Markov's, by Bayes' rule, has this fairly nice form. So you might think, oh, okay, so the transition matrix is just corresponds to terms of this type. But here's the thing. The sequence of transition matrices depends on the initial distribution, because the probability Zn equals I and Zn plus 1 equals j will be different if we have different initial distributions. So in backward time, the transition matrices, even though they still, I suppose, exist, but they depend on the initial distribution. And if we take a different initial distribution, then we're going to have a different transition matrix and different probabilities going in backward time. And this issue is true even if the original Markov chain was homogeneous. So, so this is kind of the this is kind of the issue that the transition matrices depend on the initial distribution, and so if your perspective on a Markov chain is that it should have some initial distribution and a sequence of transition matrices, that works fine in forward time, but not in backward time. So that suggests kind of what we in the paper term a dichotomy of in these two definitions, and one that's perhaps, at least my colleague Isaac Sonin thinks perhaps, well, while kind of it's a simple point that I think everyone at some level recognizes, but one that perhaps, as Isaac Sonin suggests, should be maybe a little more thought about, and people maybe should be a little bit more careful in thinking about what a Markov chain is in light of this kind of dichotomy. Now, of course, if the Markov chain is stationary, then in a sense, we have a simple formula for the Markov chain in reverse, for the transitions in reverse time. They still technically depend on the initial distribution, but now at least they'll be kind of constant over time. And of course, we know that the transition matrices for a Markov chain in reverse time are going to be the same as those in forward time if the Markov chain is reversible. That is to say, it satisfies this property. Okay, so now a little bit of history about Markov chains in backward time. So motivated by Schrodinger's analysis of the reversibility of the laws of nature, Komogorov of 1936 studied the reversibility of Markov chains. And this paper introduced both reversed and reversible Markov chains. And it's an very interesting paper, only 6 pages long, not only did it introduce reversed and reversible Markov chains, it also initiated the study of Markov chains on going forward in time, but indexed by the integers or the negative integers. So really did a lot in this one very short paper. And the next part of the talk is going to be exactly about this question of Markov chains indexed by the integers or even just the negative integers, Markov chains starting at -infinity and going forward in time. So under what conditions will they actually exist? So that's the third part of the talk. So let Sn be, so let's set up the framework we're talking about. Let Sn be a sequence of state spaces indexed by the integers. Let Pn be a sequence of transition matrices indexed by the integers. So let Z's be a sequence indexed by the integers, be a Markov chain where Zn takes values in Sn and has transition matrix Pn. That is to say, the probability Zn plus 1 is in state J, given that Zn is in state I, is the ijth coordinate of matrix Pn. So that's kind of the framework we're looking for. But the question is, well, does such a Markov chain actually exist? So as far as we know, and we did a relatively thorough study of the literature, this question has only been addressed in two papers, Kolmogorov's 1936 paper that I already mentioned, and Blackwell's 1945 paper. And in both cases, they only considered the case when the cardinality of the state spaces was finite and equal to a specific term n. By the way, if anyone is aware of any other publications on this question, please let us know. We're very interested to see if there's anything more, but we, as I said, did a fairly thorough review of the literature and could not find anything really beyond these two papers. Okay, so the answer to the question of does such a Markov chain exist in Kolmogorov 1936 under these conditions, that the answer is given as yes. And Kolmogorov further gave conditions for uniqueness. Blackwell then studied uniqueness further. Blackwell's paper also addresses other related questions about Markov chains indexed by the integers. So our goal is to kind of extend these results away from the case where the state spaces are all have the same cardinality and consider the case where the state spaces may be countably infinite and see if a Markov chain will exist in those cases. So again, let Sn be a sequence of state spaces indexed by the integers. Let Pn be a sequence of transition matrices. And so our theorem, this is a theorem just for the finite case, not for the countable case, which we'll address a little bit later in the talk. So assume that we have n sub n is the cardinality of the nth state space. We will assume that n sub n is finite, but we allow it now to change and even to approach infinity as n goes to -infinity. So for every n it's finite, but it can grow in an unbounded way near negative infinity. I suppose it can do that also near positive infinity, but that's but near positive infinity, we kind of know that's the classical theory. It's what happens near negative infinity. That's the interesting question. And then a Markov chain with these transition matrices is going to exist.
Sorry, well, the limit is less or equal to infinity. What does it
yes,
mean?
so just to emphasize that it can equal infinity. I agree. There's no real content to this statement except to emphasize that it can equal infinity, but doesn't have to. Mm-hmm. But thank you for the clarification. You're absolutely right. Mm. Okay. So, and following Kolmogorov and Blackwell in the paper, we also give necessary and sufficient conditions for the distribution of the Markov chain to be unique. But I won't present them here. You can find them in the paper. Okay, so I want to prove this theorem, and then we'll talk about the countable case, but I want to go through the proof, at least give an outline of the proof. It won't of course, get into all the details. So the first step is to transform the problem. Instead of thinking about this situation as a problem about the existence of a Markov chain, we can use Kolmogorov's extension theorem and basically transform the problem to being kind of a linear algebra exercise. So, so the idea is as follows. So first, we'll introduce this notation, D of n. D of n is the collection of probability distributions on state space S sub n. So we know since S sub n is a finite state space, any distribution on a finite state space is just going to correspond to a vector in R n sub n, the cardinality of the nth state space. And of course, we need the components to sum to 1 and be non-negative. So this is the collection of all probability distributions on state space n as represented by a vector. And so basically, Kolmogorov's extension theorem says that we just need a consistent family of distributions. So, so it suffices to show that there exists some vectors, some sequence of vectors in such that m sub n is in Dn, so corresponding to a probability, which are consistent in the sense that Mn times Pn, the nth transition matrix, gives us Pn plus 1. And of course here, P sub n corresponds to the unconditional distribution of the random variable Zn. So the probability that Zn equals I is the ith coordinate of M sub n. So now we have translated the problem from something about random variables to just finding whether or not we can find such a sequence of vectors satisfying this equation or not. So so we must show that there exists a sequence of vectors indexed by the integers. M sub n is a probability distribution on the nth state space, and it satisfies this equation. Now, in order to do this, we'll introduce, we need to introduce a multi-step probability transition matrices. So if we multiply P sub n from S to T minus 1, then we'll have a transition matrix not from state n to n plus, from n minus 1 to n, but from state S to state T. So P sub St is the transition matrix from state S to state T. And so, of course, if we have a solution to this equation, then for any ms, then for m sub s times pst will give us mt, right? So instead of going in one step from time s to time t, we take whatever we had at time s multiplied by pst, and we get the vector at time t. Okay, so now imagine that, so of course we're interested in what happens when the Markov chain starts at negative infinity, so it never has a starting point. But for the moment, let's assume we start running our Markov chain at some time s, where s is very negative number, maybe minus 100, minus 1,000, some very negative number, and some very negative number s. And then, of course, we can always start at time negative s, just then that becomes our initial time, and we go forward in time. So any distribution in d of s, which is the possible distributions at time s, so any distribution in d of s can serve as our initial distribution at time s, and then we let the Markov chain go forward in time, and then if we start with distribution ms, our distribution at time t is going to be ms times pst. So, so this is a distribution we're going to have at time t. We started with m sub s, and we can consider all possible vectors of this form, where we took some initial distribution and then multiply it by pst to see what is the distribution at time t. So let delta of s comma t be the collection of all vectors that we can have at time t if we started at time s with any initial distribution. So delta of st is the is the collection of all possible distributions at time t if we start the Markov chain at time s. Now, clearly, for any s less than t, we have this nesting that as the time when we start the Markov chain becomes more and more negative, then so as the time becomes more and more negative, then we kind of have subsets. We have fewer and fewer possible distributions that we could have. So so we have this kind of nesting. Further, it's not difficult to show that every delta of st is a compact set for every s and every t. So now what we have this kind of nesting structure, and we have that every one of the deltas is a compact set. And so by Cantor's intersection theorem, if we take the intersection over all s less than t, the resulting set, which we'll just call delta of t, is not empty. So, so this exactly corresponds. Delta of t is basically what would what distributions we can have if we start at minus infinity, right? Delta of st is all the distributions we can have if we start at state s. Delta of t then, after we took the intersection over all s, delta of t is all the distributions we can have if we start at minus infinity. And of course, the point is, by Cantor's intersection theorem, it's not empty. So we have, so there is some possible distribution at time t, even if we start at minus infinity. So this collection is not empty. And this collection of possible distributions at t, if we start at minus infinity, is not empty, but we still have to resolve, are the distributions really consistent? So we know we have some distribution at every time, but perhaps we don't have consistency. And so, but consistency is pretty easy to show. I won't go into all of the details, but we have this lemma here that says that for each mt in delta of t, there exists an mt minus 1 in delta t minus 1, such that the correct multiplication holds. And so we have a consistent, so we have consistency, and this shows that we have the right finite dimensional distributions for any finite dimensional set. And so we can use Kolmogorov's extension theorem to prove the existence of such a Markov chain. And that basically completes the proof of the theorem. As I said, in the case where the number of states is constant in time and finite, that theorem was addressed by in Kolmogorov's paper. Now, Kolmogorov's proof was not very detailed, and so when we were looking at the proof, we didn't quite understand exactly what he was doing. So we're not sure if what we're doing is exactly kind of extending his line of thought or not. But certainly seems to be along some similar lines. Okay, so so that's the proof of the theorem that there do exist, if we have finite state spaces, there do exist Markov chains indexed by the integers. Now, an interesting byproduct of that proof is that this kind of more general result. So assume we have a sequence of metric spaces, and we have a sequence of continuous transformations from Vn to Vn plus 1. And further, assume we have a sequence of non-empty compact sets, D of n, such that D of n is contained in V sub n. Then further, we'll assume that the image of Dn is contained in Dn plus 1. Then there exists points m sub n, such that n is in Z, where m sub n belongs to set D of n and satisfies this relationship. So kind of an interesting, more general result that we got from that theorem, from the proof of that theorem. And this theorem turned out to be useful for proving results for the countable case. Now, the countable case. So now let's address the countable case. So let's Sn be a sequence of state spaces, and let Pn be a sequence of stochastic transition matrices. Now we'll assume that the cardinalities of all of the Sn's are infinite for every n. In this case, it turns out that a Markov chain with the given transition matrices is not guaranteed to exist when indexed on the integers. So kind of an interesting difference between the finite case and the countable case. Here, it's not guaranteed to exist. I'll give an example at the end of the talk where we see a simple situation where the transition matrices, where the Markov chain does not exist. And the difficulty is why the previous proof isn't going to work, is that the space of all probability measures on a finite set is compact. So those D of n's that we looked at were compact. And we were always thinking about subsets of compact sets. But on a countable set, this is not compact. So the set of probability measures on a countable set is not compact. That is why we can't use the theorem that we had before. We were not going to be able to guarantee that the delta of STs are compact, and we won't be able to use, therefore, Cantor's intersection theorem. So in order to ensure that the sets are going to be compact, we're going to need a tightness condition. So, so first, before stating the tightness condition, let's just take a few seconds to think about about how stochastic matrices work in the countable case. So again, assume that each state space is now countably infinite. Let P sub n be a stochastic matrix, be a sequence of stochastic matrices, and of course now these stochastic matrices are infinite. So what it means is, well, it is basically we have an infinite collection of probability measures on a countably infinite collection of probability measures on a countably infinite space. So the probability that Zn plus 1 equals k, given that Zn equals I, is going to be the I kth coordinate of this stochastic matrix. So if we fix I and let k vary, we have a probability measure. So for every I, we have a probability measure on a countable space. So what we're going to need basically is for every probability measure, for the collection of all these probability measures given different i's, to be tight. So this is condition P. There exists an infinite set V contained in the negative integers, such that for any n in V and any epsilon positive, we can find an n sub epsilon of n, such that for any state I, we have this condition. So this is just a tightness condition. This is just a usual tightness condition. So the main thing to note is, first, we don't require the tightness condition for all of the stochastic matrices, just an infinite set of the stochastic matrices. And second, we only require separate tightness conditions for the different stochastic matrices. So that's why this n sub epsilon of n depends on which stochastic matrix we're talking about. So it's not tightness over all of them, but each one has to be tight with its own capital N sub epsilon n. And then if condition P holds, then the required Markov chain exists. In the paper, we also give a condition for uniqueness. You can find it there. And notice, though, with this theorem, it's if condition P holds, then the Markov chain exists. But P is only sufficient. It's not necessary. There are examples when condition P does not hold and the Markov chain still exists, and examples where condition P does not hold and the Markov chain does not exist. So both are possible. So this is just a sufficient condition. Whether there's a simple necessary and sufficient condition, in this case, we don't know. That's still an open problem. But maybe very briefly, let me just end with an example to show you that really there are situations where the Markov chain on Z does not exist. So that you don't think that we just needed this condition P, but no condition is needed. So the example I'll give is kind of the simplest Markov chain on Z, which is a symmetric random walk. And to see that no Markov chain exists, let's see what happens if we start at time minus n, and then we'll take the limit as n goes to minus infinity. So we'll be starting at, in that sense, at time minus infinity. So let's consider the probability that at time 0 will be in state j, given that we started in state minus n at in state I. Of course, the probability of this is going to be, well, for any path of length n, the probability is 0.5 to the power n. So it's 0.5 to the power n times the number of paths of length n from state I to state j. We can upper bound the number of paths of length n from state I to state j by the number of paths of length n starting at I without caring about where we wind up. And there's 2n, choose n such paths. And using some basic properties of binomial coefficients, we can upper bound this by c, some constant, times n to the minus half. Then, applying the law of total probability, we can find that the probability z0 equals j unconditionally will still be upper bounded by a constant times n to the minus half. And of course, if we take n going to infinity, this will approach 0. So this probability approaches 0 for every j, which means that there is no probability distribution, right? Because the probability distribution is all zeros, and a distribution that's all zeros is not a probability distribution. So that's how we can see that this is an example where a Markov chain does not exist. Okay, so here is our bibliography. Of course, this paper of Kolmogorov, which really started a lot of these ideas, as well as the paper by Blackwell, Isaac Sonin's paper where he introduced the 0-1 law, and this is our paper with all of these results. You can find it on the archive. Okay, so I'd be happy to take any questions that you have. So any questions?
May I ask a question? Actually,
Of
not a
course,
question,
yeah.
but a suggestion. So I remember that at the end of 60s, maybe beginning of 70s, there was quite a lot of activities in the theory of Markov fields. And in certain sense, no, in particular, Markov fields on integers, so on Z. And there's basically, this was done by Dobrushin. And in principle, this means that there are conditional probability from on a certain family of sets and boundaries of these sets. In certain sense, this is a kind of Markov chain evolving in both directions. Did you make a look? Maybe Sergei Pirogov can say more.
Yes, I just wanted to say that the theorem of existence of Markov chain is in some sense a one-dimensional analog of general Dobrushin's theorem on the existence of Markov field on the integer lattice. This is just the same argument.
Okay, well, thank you very much for letting me know about that work. I've seen, of course, several papers of Dobrushin in non-homogeneous Markov chains, but I'm not familiar with this area, so we'll certainly look into it. Thank you.
Sometimes it seems that it was called Averyantsov theorem.
Sorry, what's the name of the theorem?
Averyantsov theorem really proved not firstly by Averyantsov, that's a long history, but the theorem was explicit, in some sense explicit description of conditional probabilities for Markov fields. But okay, it is another story. It is not connected with the existence problem. It is another story. It's a problem of description of conditional probabilities, because for Markov chains it's very easy to say. It is matrix. But how to describe conditional probabilities for the fields, it is not so easy, but anyhow it is possible.
Okay, well, thank you very much for bringing my attention to this work, and I'll discuss it with Isaac Sonin. So it seems like a very interesting situation that's quite related here. So I very much appreciate learning about that.
Dear colleagues, please, another comments, maybe in Russian, please. So, Mikhail, thank you so much. Mikhail and Исаак, thank you so much for your report, for your talk once more. And please, it's a comments from Веретенников, Alexander Веретенников.
Oh, there's a in the chat. Have a okay.
Can you hear me?
Yes.
Okay.
Please.
Michael, you at some pages you showed at least twice the definition of what is Markov chain.
Mm-hmm.
Could you show the first place where you did it?
Here?
Okay.
Yes.
Yeah, for example, if I were to lecture for students, I would emphasize that the probability of the condition should be positive. But this is a very easy remark and trivial. However, if this past trajectory is infinitely long, is it possible that probability of this trajectory is not zero? And then is it not a problem? If you define with sigma algebras, then of course you can reformulate it and there is no problem. But in this form, I hesitate.
Yes, you're absolutely right. Yes, I did not think of it. I mean, of course, the concept still makes sense as you said in the definition in terms of sigma algebras. But you're right. We are conditioning on a set of probability zero, which at minimum is it makes it difficult to interpret and is not very. Yes, I agree with you. That for this definition, one should use sigma algebras. Yes, thank you very much for pointing that out.
That's it.
Okay. Any other questions?
Mikhail, I have one question, and could you show your last slide? Not reference, but the last slide of your presentation.
Okay. Okay.
Here. And could you say something? You consider a symmetric random walk on dimension 1, lattice dimension 1.
Mm-hmm.
I think that it is known result. What you can say about the other dimensions? about the other dimensions. For example, the dimensions 2, 3, and other dimensions.
Elena, I can ask immediately. You will have n in the power minus d over 2 in the right-hand side. It is very easy to prove using local limit theorem, for example.
Yes, yes, of course. I would like to say about it. Yes. Thanks.
Okay. Yeah, so we did not consider that, but that's an interesting point. Certainly, I guess people here are far more experts than I am. I can't look at this and say that it would be exactly n to the minus d over 2, but that certainly feels right. And of course, I recognize that the people here know that. So thank you very much for kind of extending the example.
And of course, you write about symmetric random walk on ZD, but of course, it depends on does this symmetric random walk have a finite or infinite variance of jumps on something else. Here you, of course, consider the finite variances, as I understand.
Yes, I just consider the situation where we take one step with probability half, we take a step forward or backwards with just.
And of course, this depends. There are many papers, and for these examples, we, for example, have to know the transition probability of such process. It's enough, I think, to answer this question. What about another? What about, please, in other comments, please? Dear colleagues, thank you very much for your report once more. And we will be glad to see you in our seminars in future. Thank you. Thank you for your talk once more. Maybe our comments are useful.
Certainly. Certainly, thank you very much for giving me the opportunity to speak here, and for the comments. They've been really very very useful ways of extending this example and give us a very interesting literature to take a closer look at and see the connections with it. So that the comments have been really very, very useful. So thank you to everyone who gave comments and everyone who just came for the talk, and thank you for giving me the opportunity to talk here today.
Дорогие коллеги, тогда позвольте мне сегодня, если нет еще вопросов или комментариев каких-то, никто не хочет сказать какие-то слова еще вот по поводу доклада, тогда у нас, позвольте сказать о нашей программе. Значит, сегодня у нас 18:10 ломоносовские чтения для молодых сотрудников. В следующую среду у нас будет, как всегда, большой кафедральный семинар в 16:45, и доклад будет такой более статистический. Будут выступать люди из Новосибирска, а вечером у нас будут ломоносовские чтения, будут представлены доклады Болдина, Кондратенко и Малышева. То есть у нас в следующий раз такая достаточно большая программа. Будет часовой семинар, и потом еще плюс 18:10 вместо аспирантского коллоквиума ломоносовские чтения. Все, тогда спасибо всем, и мы завершаем наш семинар.
Спасибо, до свидания.
До свидания.
До свидания, до свидания.